Today, we're starting a mini-series on learning models in economics. This is a slight departure from the factor models that we've just been studying, but there are some similarities that we'll get into later on in the series. Learning models let us estimate economic fundamentals in settings where the decision makers don't have perfect information. Instead, they have to update information about the things that they're making decisions over as new information arrives. And as we'll see as we get into this series, these types of models have application in almost every subfield of economics. Let's start by formalizing what we mean by imperfect information and introduce the concept of noisy signals. As I mentioned, imperfect information abounds in economics and in real life. You can think of events in life as being noisy signals, and also the adage that it's better to be lucky than good. What does this have to do with imperfect information? Well, how do we know if something is lucky or good? If we're visiting a restaurant and we had a good meal, how do we know that that's actually a good restaurant and not just a one-off favorable draw? So it could be the case that we got their best dish on their best night, and if we go back, we're going to be underwhelmed in the future. So now that we have some concept of noisy signals and favorable draws versus consistent performance, let's talk about how we'd actually estimate a model where a person has imperfect information. And the analogy that we could make is to dynamic discrete choice models, because people can't see the future in those models, so they have to take expectations over what they think will happen based on what they can see in the moment. And these are taking the form of expectations about preference shocks in the future or state transitions in the future. And then we have this Emacs formula where we can compute their expectations, and then we have some distributional assumption on epsilon that is probably way too strong, but is the only way to really make these things tractable. So we'll take this same type of idea and map it to the noisy signal problem. And so let's set up this problem. We have an agent that's trying to learn something, and this something we can encapsulate with the random variable a. So agent I is trying to learn about AI, A sub I, and we can just assume that A is continuous and drawn from some CDF. And what's important to emphasize is that the agent does not know the exact value of A, but does have some belief about it. And we denote that with E sub t of A sub I. And the E sub t just emphasizes that this belief might change over time, depending on how the information set evolves. And in particular, there's a signal, S sub it, that may arrive and provide more information about A to the agent. And in particular, this signal S is noisy, and so we can write it as an additive sum of A sub I and epsilon sub it. And this epsilon it is pure noise. It's not correlated with anything. It's just there as noise infusion. So the agent can take the information that was in S sub it and use it to update his belief about A sub I. And we would call that updated belief E sub t plus 1 of A sub I. And then we can just have this process repeat itself for however many signals there are to be received. So if we go back to the restaurant example, A sub I could be the quality of the restaurant, and every time I go to the restaurant and order something new, I'm going to get a new draw from S sub it. So what's happening is AI is always the same across all these signals, but what's different is the noise. So I might get a negative value of epsilon one time I go to the restaurant, I might get a positive value the next time. And I can make assumptions about the average value of this across all time periods, and then that can maybe provide some information. So let's formalize that a little bit more. We can normalize the average values of both A and epsilon to be 0 for all individuals and all time periods. And then under these assumptions and the assumption that epsilon is white noise, we can write down the variance of the signal as being the sum of the variances of each of the components. So A is going to have some population variance, call it sigma squared A. Epsilon's going to have some population variance, call it sigma squared epsilon. We assume that the agent knows both of these quantities, but just doesn't know their particular value of A. And then the only thing the agent can see is S, which is the sum of the two. So naturally, you can see how you would need to get multiple draws from the same signal to be able to start to separate what's signal and what's noise. And then a helpful quantity that we might find useful is called the signal to noise ratio. And this is just the ratio of these two variances, and it's a measure of the quality of the signal. So if a signal has a high signal to noise ratio, then I need fewer signals to infer the value of A. Whereas if it's a very low signal to noise ratio, then I'm going to have trouble distinguishing it in a short period of time. So we want the value of this signal to noise ratio to be as high as possible if we want to ascertain the true value of A. And then another quantity that we might see in some formulas in the future is called the variance ratio, which is just the variance of the signal divided by the variance of the noise. And these can be helpful if we're thinking about how do we write down formulas that we could then take to some data to test the implications of this model. That's a little bit about the setup for these learning models. I hope you can start to see how these could be useful in a variety of economics contexts. And as we've talked about these principles, you might have seen some things that are reminiscent of factor models, which we've covered previously. In particular, that there's a composite error term that has pure noise and something else. And in the next video, we'll make a complete comparison and contrasting between factor models and learning models to help solidify your foundational understanding. So hope you've enjoyed this video and hope to see you in the next one.